Hey guys, my name is Schwartz, and I'm here presenting today my final physics video. The purpose of this video is to compare the momentum principle and the energy principle and use both to calculate the final velocity of a sphere rolling down a hill. I'm sure many of you guys remember this question from our test, and I'm going to show you how both of the systems can be used and how they correlate to find this answer. Well, first thing I did was I rolled the ball down a hill, give my axis 0, 0 starting right here. If you get a graph like this for the y direction, model this in tracker, both in the y direction rolling down here, the slope is right here because it kind of bounces the table with bounce, and in the x, I also model this in the x direction. As you can see, there's an arc to this because it increases. As you can see, basically it goes farther down in the x direction and farther down in the y direction. The acceleration increases due to the forces acting on the system. From here, I decided to go and model this. After this, I went ahead and I did this using the momentum principle. The first thing I did was you have to calculate the net force acting on the system. Well, there's obviously the force of gravity acting on the ball, the starting position, and after that there's a normal force. As you can see right here, here's how you can calculate the normal force acting on the ball. For inertia, and then once given this, you can calculate theta by taking the first thing I did was I used the momentum principle of the height. I had to select my time period, which was the time it took from it to roll from the top of the hill to the bottom of the hill. And the next thing I did was I figured out the components of the forces acting on the system, like we've done all year. The forces is the force of gravity and 0.140 kilograms. I started force of gravity you already know, but how do we calculate the normal force? Well, basically you have to set up a graph like this. I also have some data, inertia right here. Here you can find the components principle, just like the testament over the energy principle. And data basically going to relate to the momentum principle and the tangent principle, how they can both be negative 1 inverse tangent of the height over the length. First things first, I decided to use the momentum principle. So here, I went ahead and after this, I plugged that in how long it took normal force, and then I found the top to the bottom, which is just adding these forces together. And then from here, I did the velocity update and the position update, which we've been doing all year. Calculate the components of the forces, and then we add them together to get F net. After that, I ended up with the result. State how ball's velocity changes based on F net times delta t. You end up like a graph like this when you graph essentially the initial velocity plus the acceleration times delta t, and the red after that we do the position update formula. This graph makes sense. Not only is it just like our curves shown in tracker, but because of the arc, the ball is accelerating. But the green line is longer because the ball goes farther in the x direction than it does in the y direction, which makes sense when you look at the type of hill I rolled it on the table. It was smaller in the y direction and larger in the x direction. So by the time you saw from the video, the table, the x the height was obviously lower than the length, so the correlation of these graphs makes sense. Obviously, it fell lower height. I then used this to calculate the final velocity of the ball, which gave me, ended up being 4.99 meters per second. As you can see right here. And also there's 4.99 meters per second in both directions because we tried to use the energy principle to find the final velocity of the ball. In order to do this, we used a real system and the x and y direction. As time continued, the forces increased, and so basically we ended up getting it into this form where the final velocity and y direction, and that's why you see that gravity height over 7 right here. This because it's a solid sphere, and the cross ball I use is solid sphere, so the inertia are the same, run this because of that, it's going to end up being the same for Python. When I did this, I ended up with a final velocity of 4.39 meters per second. As you can see, these are pretty close. So obviously there is a correlation between the energy principle and I end up with a final velocity of 4.99 where do my errors come from? Well, the errors that could have contributed to this is I did that using possibly when I'm trying to figure out the amount of time it went from the top of the rolling platform to the bottom of the platform. Well, if I'm a little bit energy principle, like if I overestimate or underestimate it, this will greatly affect the change of velocity and the momentum principle. If it's rolling down for a longer time, the speed is going to be longer. So it's pretty difficult to estimate that amount of time delta gravitational, which equals the work. and there's only a small amount of air there, the work of gravity in the ball. Now, I went ahead and also modeled, if you go farther down, it gives you the final velocity. Using the Python as well. Basically, this and I gave this by using K-rotation in the form of inertia, which we also use here in the problem. Now, when I plug this, the values and I also represented translational 4.39 meters per second compared to 4.99 meters per second using the I went ahead and graphed this. Now, this is a slight error. As you can see, the results are fairly similar, which shows the correlation between the two of them and accuracy. But the reason for the inaccuracy is because they have to add up the total work on the real system, take the time that the ball goes from the top of the table to the bottom. It's really hard to estimate the work done by gravity. And also the green line represents the translational kinetic energy, and the red line represents speed or rotational speed. It might be Python as you can see, the translational that's one of the reasons why it's difficult to get it exactly on. And that just shows kind of now the way what I did after that can be applied to evaluate a system and not just the momentum principle. Energies. I hope you guys enjoyed my video and thank you very much. Energy. And as you can see, let me run this one more time for you. Boom. The green line represents the translational kinetic energy, and the red line represents the rotational kinetic energy. As you can see, they both add up to equal the total work acting on the system, and the translational kinetic energy ends up being greater, which makes sense because it ends up moving farther. And yeah, I hope you guys enjoyed my lab, and I hope you guys can now see the correlation between the energy principle and momentum principle, and how they can both be used to answer questions about our system. Thank you very much.